Alrighty, everybody. So thank you for joining us today. My name is Wyatt Pena, and I'm the Director of Operations at Ridgetop Group. And today we have a very special webinar presented by Ridgetop and distinguished staff scientist, Dr. Kevin Gering at Idaho National Laboratory. Today in the conference room, I am joined by my coworkers and team, Jan Traficante, Virginia Land, Clay Hunt, Arch Natharni, and Christopher Curdy. So I'll first start out by just giving a brief overview on the agenda. So we will be presenting on the Advanced Electrolyte Model, and we'll start out with a little bit about Ridgetop Group and Idaho National Laboratory, some general electrification challenges within industry, an AEM introduction video, and then I will turn it over to Dr. Kevin Gering to cover what is the Advanced Electrolyte Model and the technology overview, some examples from recent applications, and then I'll pick it up for a live software demonstration, discuss the relationship between AEM and another complementary technology called CellSage, and then the customer market segments and collaboration opportunities that we're looking to engage with industry on, and then we'll have a summary and some questions. A little bit about Ridgetop Group and INL. So Ridgetop is located in Tucson, Arizona, and we were founded in the year 2000. We primarily service the aerospace, automotive, industrial, and government market segments. And we are a technology leader in reliability engineering, quality assurance, condition-based maintenance, prognostic health management, and integrated vehicle health management. We're also a AS9100D and ISO 9001 certified quality facility, certified by the Management Certification Agency of North America. With that, we specialize a lot of our background and expertise is for engineering design services, designing circuitry for harsh environments, prognostics, and then developing hardware, firmware, and software elements for CBM, PHM, and IBHM applications. And a little bit about INL. So they are a part of the U.S. Department of Energy's complex national laboratories, and they are also one of the nation's leading centers for nuclear energy research and development. So some general electrification challenges within industry are mentioned here on this slide. So we know as North America and even the whole world continues to try to shift to clean renewable energies, batteries and battery energy storage is going to continue to play a key role in that. But in North America in particular, we do recognize the challenges with our battery supply chain, extraction of raw materials for the battery manufacturers, the lack of EV charging infrastructure, and then the upfront investment costs for clean energy projects. There's also a big challenge with the application of standards and best practices for second use applications, and then the time to market to develop new battery chemistries for unique applications. So there's clearly a pressing need for modeling simulation analysis tools like the collection we have developed at INL and at Ridgetop with the Advanced Electrolyte Model, CellSage, and our adaptive remaining useful life estimation software, ARUL. So this slide covers some of the different aspects of the lithium-ion battery life cycle and where we focus our collective efforts between Ridgetop and INL. So we develop these modeling simulation analysis software tools for battery manufacturing, battery use, and second use applications. And today's webinar for AEM will be focusing on how the different combinations of salts and solvents and additives play a key role in extending the operational life of lithium-ion batteries. So here we have a short video.
Batteries are becoming more abundant in our everyday world. They power everything from cell phones to electric vehicles to grid-scale storage for renewable energy. Battery design must be tailored to each application to optimize performance, longevity, and the product's weight. To this end, Kevin Gering, a distinguished Idaho National Laboratory scientist, created Advanced Electrolyte Model, or AEM.
AEM is a molecular-based computer simulation program for discovering and optimizing electrolyte formulations in batteries to improve battery performance.
With AEM, researchers can determine over 100 property metrics virtually. It allows changes to the profile of a battery on the molecular level without having to build a prototype. By accurately predicting the performance of complex electrolyte formulations, AEM helps developers produce an efficient battery system and reduce energy storage costs. AEM can help capture and store renewable energy from sources like wind and solar more efficiently and at varying conditions. AEM also provides time and cost-saving benefits to accelerate electric vehicle and grid-scale battery system development.
AEM provides vast possibilities with over 50 solvents and nearly 40 salts. This creates millions of combinations, enabling users to find ideal candidates for their specific needs while considering the merits of various electrolyte options.
Each AEM analysis generates more than 20 reports, covering aspects like transport, thermodynamics, physical properties, thermophysical, kinetic, molecular, and macroscale metrics. This comprehensive information empowers researchers to make well-informed decisions on battery chemistry.
AEM's extensive predicted property sets span broad ranges of composition and temperature and are crucial for understanding battery electrolyte performance. Over 100 property metrics are generated and reported with each simulation. This includes ionic transport functionalities, thermodynamic and thermophysical terms, properties tied to molecular processes at interfaces such as lithium desolvation, electrolyte permeation into electrodes, and many more. AEM significantly accelerates battery development, bringing advanced battery applications to market more quickly.
Success of AEM can be seen by its increased adoption, where several large corporations and universities have licensed AEM to help accelerate their battery programs. The Advanced Electrolyte Model, helping create a world powered by clean energy.
So now I'll turn it over to Dr. Kevin Gering to discuss what is the Advanced Electrolyte Model. And just as some general guidelines and questions that may come up, feel free to note down the slide number and we can discuss those during the Q&A at the end of today's webinar.
Okay, thank you, Wyatt. This is Kevin Gering from INL. Thank you for joining today, and I hope you enjoy the presentation and the material that we're delivering. So what is AEM? The video just touched upon this. AEM is molecular-based chemical physics property prediction software. It's designed for electrolyte solutions, and its application is most often battery electrolyte screening and optimization, although the outputs from AEM can apply to other fields as well. The model produces over 100 property metrics per simulation, and this ranges from molecular to macroscale properties, and it has a wide range of components, and this is growing week by week. It has over 50 solvents at this point and nearly 40 salts. These cover lithium-ion type battery systems, aqueous systems, as well as sodium-ion type electrolytes. The model is very fast due to the chemical physics framework. It runs most cases in less than 10 seconds, and these can cover thousands of different conditions of concentration and temperature. Optimization runs take longer. The inputs are very customizable. The user can specify up to 10 solvents in a mix system and 2 salts per electrolyte mixture. And we allow wide ranges of salt concentration from basically infinite dilution to saturation. Temperature generally ranges from about -40 to 80 degrees for most cases. The accuracy that is maintained by the model is within plus or minus 5% average deviation. That is our goal. Sometimes it's better than that. Sometimes it's a little worse than that. So it might vary a little bit with the system, but that's our overarching goal for the predicted properties. The outputs cover 20 different reports per run, and each report contains different types of property categories. Next slide. The current version of AEM is actually 2.23.1 was released this month. And this is compatible with Windows basically 7 through 11 and can be adaptable to Mac systems. When you receive the software, the operating and executable files comprise generally less than 500 megabytes. The report files that are generated can vary in size depending on the type of user inputs. So in practical terms, this can be, say, between 5 and 500 megabytes per file. When it comes to service for the software, INL provides initial guidance and technical type guidance on software usage and will help oversee periodic updates to the AEM during the license term. These updates might include things like increased components within the library and additional calculational features. Ridgetop Group will facilitate the licensing and software distribution and notification of updates. Next slide. Just going to walk through the categories of AEM properties that are predicted with each simulation. Starting at the top and going clockwise around, we have thermodynamic properties. These are useful in different types of macro cell models or macro scale models for cells, like a Newman model, osmotic coefficients, activity coefficients, different things regarding thermodynamics like species equilibria amongst the different salt type consequences. Next, we have ion solvation terms such as the solvated ion sizes, solvation numbers, both cation and anion. We also have the binding energies between solvent and ions, as well as the desolvation energy for the cation. There's also a term called communal solvation, which covers things like multidentate solvation when a solvent molecule is participating in solvating at least 2 ions at the same time. We have permittivity terms that are necessary to produce the rigor and resolution of ion association as we increase salt content. And then we have other analyses in the middle toward the bottom. Walden analysis, things like osmotic pressure, surface charge effects on electrolyte permittivity, ionic hopping, and activation energies. Then the last few categories, we have rheological terms that you might envision are important toward things like electrolyte penetration into porous media, thermophysical properties, enthalpy, thermal conductivity, and heat capacity. And last but not least, transport properties covering viscosity, conductivity, diffusivity, and the cation transference number. Next slide. Okay, as has been mentioned, the AEM produces a number of different reports as it runs. Each report has a different collection of output properties that are, we would consider to be genomic level information. And so this is a very solid foundation for learning inside and out the different attributes of different electrolyte systems. Recently, we've added 2 new reports that cover what is can be summarized as microstate structure type terms. Next slide. Okay, here's a glimpse of the library currently within AEM. As was noted, it has over 50 solvents of different types, carbonates, esters, ethers, nitriles, phosphazines, and then other sulfur-containing type compounds. And then on the salt category, we have nearly 40 salts that are listed. The ones on the left column is the general list for battery electrolytes, and the ones on the right are designated for aqueous systems. Next slide. Okay, so this is given just to provide an idea of what complexity lies behind some of these properties. When it comes to electrolyte conductivity, there's several contributions to what you actually see listed as a number when you take a measurement, because of the complexity within the system and how all things are interrelated depending on how the species are interacting with each other. So within this particular focus, we see that electrolyte conductivity is impacted by viscosity, which is kind of an obvious thing if you look at the Stokes equation for ionic conductivity. But there's several things that influence viscosity in and of itself, such as ion solvation and sizes of the ions and other factors that fall behind viscosity. So going around looking at some of these contributions, there's probably, I would say, 6 or 7 that are quantified within the model as it runs, and there's a special report dedicated to these different factors that contribute to conductivity. Next slide. Okay, here we have some cases where we've validated the model against published literature. This is only a small subset of what we could be providing. It's just that we don't have time to show every single validation case, but these cover some of the, I would say, more important metrics for transport properties. On the upper left, we have diffusivity type information that is provided. The symbols are the experimental data, and then the solid lines or dashed lines are the AEM predictions. As we go to the right, we see examples of conductivity that is predicted for different cases of looking at methyl acetate with or without ECDMC. So this study was done with Jeff Don's group out of Dalhousie University, and we saw some very good agreement there with their data. And then as we go toward the bottom, we have bottom right, we have conductivity for the ECEMC LiPF6 system that originated out of Oregon National Laboratory. And then to the bottom left, we have viscosity predictions from Merck. The data is from Merck Corporation and predictions by AEM. Next slide. Okay, just thought I'd show a little more granularity for some of the terms. For diffusivity, the overall approach is a Nernst-Einstein expression that's used for the different ionic and ion-associated species. So every species that's calculated, determined to be present due to thermodynamic equilibrium has diffusivity values calculated for it. When it comes to the solvent, we use an Einstein-Stokes expression. The total salt diffusivity is gotten through a Nernst stoichiometric average given there in that first equation. The apparent diffusivity is used by obtained by starting with the Nernst and applying a thermodynamic factor to that. This factor has been developed and published before by John Newman. So this is a well-known way to condition the diffusivity for the thermodynamic effects that are in solution for batteries. So, and then these plots on the left, the two in the middle are the different species type of diffusivities given for the salt. So these are the Nernst average values given for 3 different electrolytes, given in black, red, and green. These represent different temperatures for the ECDMC system, 0, 20, and 40 degrees. And then on the right-hand side, we have the apparent diffusivities that are calculated for the same systems. Okay, next slide. So equally important to battery electrolytes is what happens with the solvated lithium, or I should say cation in general, as it shuttles back and forth between the electrodes during cycling. So it has to become desolvated in order for it to be inserted into the active host, either the anode or cathode. So there's a cost thermodynamically or energetically to do that, as well as kinetically or time-based. As we follow this lithium here and start at the left-hand side, the lithium is a little blue sphere and the solvent are the green ellipsoidal type shapes that are shown there. As we march to the right and shed each solvator, there's a binding energy and a delta T that's associated with that. So there's a kinetic analysis of this process as well as thermodynamic. If you sum up all of the delta binding energies and delta times, you get your costs for the lithium desolvating, which is a good selection criteria for different electrolytes. You'd like to minimize that to reduce the energetic requirement for preparing the lithium to enter the host. Next slide. So there's different metrics of solvation that are provided by the model. I will just give a brief overview of these. So first of all, we have at the upper left panel, lithium solvation energy at equilibrium. So this would be like the solvated lithium that is just hanging out there in solution at an equilibrium state, generally driven by concentration and temperature. So as we go and look at the x-axis and go up in salt concentration, that solvation energy tends to drop because there's fewer solvators per lithium as you increase the salt concentration. So we have 4 different electrolytes shown here, ranging from a baseline, which is a carbonate-based system, to others that are designed more for fast charge applications. So the panel right next to it is the net ligand-wise lithium desolvation energy plot. And that's when, that harkens back to the previous slide. As you start to pick off solvators one by one, the binding energy of the remaining solvents around the lithium gets a little bigger because their distance of approach, or their standoff distance between center of lithium ion to center of the polar moiety within the solvent, starts to decrease. So that increases the binding energy. So that's why these values, net ligand-wise desolvation energy, are higher than what you saw in the left panel, because of we're sequentially taking off these solvators. So as we go down to the plots below, we also have the net ligand lithium desolvation time. Again, this is kind of mirroring what we're seeing above with the ligand-wise desolvation energy. And then we have the total lithium solvation number in the lower right panel, which is kind of a starting point. And again, this is another indicator of relative strength of solvation between a given set of solvents and lithium, and how it might be screened and optimized for particular applications. Okay, next slide. AEM also produces a suite of thermophysical properties. I've shown here just a very high level view of these 3 properties. Electrolyte thermal conductivity. We use structure function relationships to derive the pure solvent and solvent mixed thermal conductivities. And then we add an electrostatic contribution from the addition of salt, and that's driven by chemical physics formula that are tuned into the attributes of the solvated lithium and counter ion, or whatever the salt might be. It doesn't have to be lithium based, but so the net or total expression for thermal conductivity is the addition of those 2 terms. As we go down, there's a relative molal enthalpy, sometimes referred to as heat of dissolution, that's calculated. And this is derived directly from the thermodynamic term osmotic coefficient, the phi of m. So it's that over dt. And then we also have the presence of the activity coefficient, gamma plus minus. Through that, we're able to see the change in enthalpy as we add salt to the solvent system. From that, we can easily derive the excess heat capacity for the system. If we add that to the native heat capacity of the pure solvents, then we have the total heat capacity for the system. These, I must tell you that these types of properties are very, very sparingly published. They're almost impossible to find for any extent for contemporary electrolyte systems. So this is a big advantage for AEM to provide this type of insight to battery users, because if you want to design thermal management around your choice of materials, including the electrolyte, and I would say especially the electrolyte, then this is indispensable for giving you numbers for these types of properties. Next slide. Okay, here's a glimpse of some of these properties plotted up. On the left, we have thermal conductivity for a number of different electrolyte choices. In our program that we're doing with the Department of Energy, we're looking at electrolytes for fast charge cell architectures. And so a lot of what you see there are different choices that we've derived through AEM. We see that the thermal conductivity drops as you increase salt concentration. And that's because the salt ions are attenuating the vibrational modes of the solvent and making the thermal conductance a little less. In the middle, we have the mole enthalpy plotted up. We see in some cases it can go negative, which is perfectly viable in thermodynamics, and then it can increase and become more positive. And then lastly, we have excess heat capacity listed for one of our electrolytes called B26. It's a multi-solvent fast charge electrolyte. We show how that heat capacity changes over concentration and temperature. Next slide. Okay, we're going to talk a little bit about using AEM to help design and screen electrolytes for battery fast charge applications. Next slide. Okay, so one thing we wanted to look at was what makes a electrolyte successful when it comes to fast charging. It's not enough just to seek out a low viscosity system. If you're trying to do charging at rates that are like a 6C rate, which equilibrates to a 10-minute charge from an empty battery to a full, you have to have something more than just low viscosity, because there's other factors that impact the success of that fast charge protocol. So in our case, we're looking at highly concentrated electrolytes, and this would be something that would be, say, between 2 to 4 molal salt within the electrolyte. And because of that, you have advantages that emerge as you go to high salt concentration. So in our cases, we've developed a suite of what we call HCEs, high concentrated electrolytes, that can be designed and tailored toward particular materials. So in our case, in our fast charge program for DOE, they're using thick electrodes. So these are approaching like 80 micron laminate thickness for both cathode and anode. So that is kind of a very challenging set of requirements to be able to maintain fast charge conditions when you have that kind of thick electrode structure to have the electrolyte work within. So given that case, we have to kind of balance transport type behavior with desolvation type behavior. So in our case, we found systems that are not only low viscosity, but possess higher conductivity at higher concentrations. So the window of conductivity is wider. Also, they have higher salt diffusivity than the baseline carbonate system. And they also have lower desolvation energy at low salt concentration. So when you run a cell under fast charge, you have a depletion of electrolyte on the anode side and an enrichment of electrolyte on the cathode side. That depletion on the anode side forces the desolvation energy to be higher, because you're always going to be progressing along those curves. If you go to the very bottom curve here on the right, as you deplete the electrolyte on the anode side, you're climbing that curve toward the left. And so you want the lowest desolvation energy possible with your choice of electrolyte at that point. So the one that's shown in green, the HCE 13, has desolvation energies that are at least 10% lower, if not 15, than some of the other choices there that are shown. So that tells us automatically this is going to be a good HCE for fast charge systems. Okay, next slide. So this kind of reiterates what I said as far as paying attention to what happens to the electrolyte during fast charge. These are called concentration polarization plots. And this is what happens to the electrolyte as you run it through a kind of an aggressive charge protocol. In this case, it's a 6C charge. And this was taken after like 100 or 200 seconds into the 6C charge condition, and showing how the electrolyte is starting to polarize and form these different concentration gradients. So this was provided, these profiles were provided by Andrew Koklischer out of NREL. Andrew and I worked together on this fast charge program for DOE, and I provide him the electrolyte properties, and he runs his cell model and then gets out these types of profiles. So what we see here as we go and look at the left-hand side where the anode is, what happens with these profiles gets worse for lithium desolvation. And as we go to the right, through the separator and into the cathode side, what happens there becomes much worse for ionic transport. So these are the things that you have to pay attention to when it comes to designing electrolytes for particular applications. And it has to be done holistically with the cell materials like the electrodes and the separator, because everything works in concert. and is interdependent. Okay, next slide. So taking that same plot that we just saw, and here it is on the left-hand side, we can march along each of these concentration polarization curve and find the electrolyte property at that point. And that's what we've done. We've plotted different properties, transport properties in the middle panel here, ranging from viscosity, conductivity, cation transference, and also the fraction of salt as single ions. We'll just look at the conductivity values, which are the squares. So for the Gen 2 system, which is a carbonate EC, EMC, LiPF6, if we follow the red squares on that, we see that the conductivity becomes very low toward the anode side. And this is a log scale, so please note that there's like 3 orders magnitude or so represented in this plot. So anode side Gen 2 electrolyte has very low conductivity, go up, and within the separator is where it becomes its maximum value. And then as you go toward the cathode, and the cathode becomes basically underutilized because there's a stagnation of salt near it or within it, the conductivity drops again to fairly low values. So compare that to the other 2 electrolytes, B26 and HCE13, which are the green and blue squares. They remain relatively high across the cell. So there's not a lot of change in properties as we go across. There are some changes, but not nearly as dramatic as what we saw with the Gen 2. So it's going to be more well-behaved. You're going to be able to sustain the charge conditions longer with these types of electrolytes than you could with the baseline. And on the right-hand side, we have some diffusivity shown for these 3 electrolytes. On the top, we have the solvent diffusivity. We see how that varies across the cell. Now on the bottom, we have the salt diffusivity. Okay, next slide. There we go. So I'm just going to mention this. We're kind of running a little bit short on time. So we had a recent addition of a new calculational platform within AEM, and this covers microstate structure. So essentially what that is solvent and salt partitioning within the electrolytes. This is driven primarily from behavior due to ion solvation, whether it's simple or complex. Simple meaning single ion, complex meaning multidentate type bridging, and multi-ion complexes being solvated. Also contributing to the microstate structure are things like ion association. So there's different combinations of ion pairs, triple ions, and more complex aggregates that can appear as you add salt to a particular choice of electrolyte solvents. And this is very much tied into what the attributes are of the solvent and salts, as well as things like temperature and also the proportion of all the different components. Okay, next slide. Okay, I'm going to step through these real quickly. So this is a summary of how the solvent starts to be partitioned or has different regions of existence within electrolytes as you add salt to different electrolyte choices. So as we go A, B, C, D, the permittivity of that, or dielectric constant, starts to decrease across those 4 choices. So A is the highest, D is the lowest permittivity. The solid line here is the free solvent that remains. In other words, it's not engaged in solvation of anything. As we start to add salt, we see that drops quickly, and then we have the solvating solvent in the non-aggregate, I would say single ion type solvating region is the dashed or dotted line. And then as we go to the heavy dashed line, that is the solvent engaged in the multidentate type bridging type behaviors. So that tends to increase quite a bit as you go to the highest salt, whereas the solvent activity driven free solvent tends to plateau a little bit in some cases, but still diminishing. And then the solvating solvent as applied to free single ions almost completely disappears in some cases. Okay, next slide. This is kind of the counterpart, but what's happening with the salt. So when it comes to the Salt that is present as single ions, that's the solid line. Salt within the communal solvation regions increases quite a bit as you add salt, sometimes be occupying 100% by the time you get to a particular salt concentration. Okay, next slide. These are the corresponding cation solvation numbers. I'm showing the cation as free ions in the solid lines, cations in the communal solvation region, and the dotted lines, and then the cation proportional average solvation numbers in the heavy dashed line. This has a direct influence on the next slide. Go ahead and move there. So there's a direct correspondence between the desolvation energy and the starting solvation numbers. Okay, next. Finally, we have the bulk average solvation numbers, which this can be, there's a level of comparison that can be done between this and like radial distribution function type of information, where the population of solvent residing with the aggregates and complexes that are formed by ions has particular numbers. And so this can be readily looked up here and compared to those types of RDF numbers. Okay, next slide.
Okay, so now we'll go ahead and get started with a live software demo for a So this is the graphical user interface of the Advanced Electrolyte Model. So previously, the program architecture was based on a command line interface as opposed to a graphical user interface. And this GUI allows the user to be able to intuitively enter each of the input conditions and also preload previously run simulations, saving a lot of time and energy when trying to run particular combinations of salts and solvents and other input conditions for a particular simulation. So the program, as Kevin had mentioned, is very, very fast, and it can run hundreds of thousands of calculations in a matter of seconds. So here we'll run our first example where we previously built in the import function to load a collection of solvents here. So we have an ester here with the ethyl propionate, and then DMC, EC, and then for the salts we have our LiPFS6, and then our temperature settings, we have a range from -30°C to 60°C, and we'll have our temperature steps with a 5-degree step here. For the method for handling triple ion stability, we'll use the default settings for that. And then the electrolyte ingress into pores, we'll use a contact angle of 35, a total pore length of 20 microns, and then the salt concentration of interest of 1.5. And at this point, we have entered all of the simulation conditions for example 1, but the program also supports the ability for surface charge, attenuated electrolyte permittivity or gate, and then double layer calculations as well. So here we are running the software program, and it should be completed momentarily. And we can now look at some of the built-in text previewing for several of the different reports. So as we talked about, there are over 20 different reports with key information that allow you to analyze the outputs of a. You also get a summary of all of your input conditions, and you can preload that back in if you would like to change maybe 1 or 2 parameters for a particular simulation. And then you can copy and paste certain data tables into other programs, such as maybe Excel or MATLAB for additional analysis and plotting capabilities. And then we also have a data visualization capability to look at certain types of data outputs. So we'll look at a particular combination of the salts and the diffusivity outputs here. But you can dynamically select what is on your x-axis versus your y-axis for the different outputs that are incorporated into AEM. So we also have the ability to determine the version number, as well as if the user needs help, we can create a support ticket or open up the user guide in the software platform. So this is just kind of a quick overview on the AEM graphical user interface, which has been developed by Ridgetop as a part of our partnership with Idaho National Laboratory. Getting back to our slides here. Through that demo, we quickly kind of just went through some of the graphical user interface inputs, as well as some of the outputs, both in the text reports and then some of the data plotting capabilities, which are all now available through the latest version of AEM. So looking forward, some of the existing customer market segments that we're currently focused on is obviously with battery manufacturers, robotics industry, EV manufacturers and suppliers, grid energy storage, power tool industries, and then universities, researchers, and government agencies. The software is available through an annual and term-based software license agreement, and that can be, a quote can be provided by Ridgetop, as we are the exclusive distribution partner for AEM. We also have another very complementary technology, which is called CellSage, and that is where a lot of our collaboration opportunities will be focused on in the near term. So we're looking for industry and government and university partners to help evaluate these different software tools for their unique applications, and also taking some of the outputs from AEM and using that to simulate synthetic data that can be used for CellSage, which takes cycle life testing data to represent how particular battery would age and degrade in different use cases. So whether it be an EV use case or a grid energy storage use case, CellSage operates on the principle of already designed and tested cells, and AEM can help us generate data for cells of unique electrolyte combinations that have not already been manufactured and in production yet. So with that, we hope to conduct new research and publish joint papers or case studies based on the current and expected future use of the software platform. So in summary, I think we will still have a few minutes here for a Q&A. And so AEM is an electrolyte selection for new cell chemistries is tedious, prolonged, and expensive. So that's one of the main challenges that AEM addresses. And it's a tool for rapid screening and characterization and optimization of electrolytes. And I think we might have downplayed some of the testing and research that has been done for AEM over its development life cycle. So it has been extensively tested and evaluated by several industry partners. And Jeff Don has also worked with Kevin to publish a handful of papers around this innovative technology. And Jeff Don is actually one of the pioneering developers and researchers for lithium-ion batteries. So most of the modern lithium-ion batteries and the work that is being done, even with his partnership that he established with Tesla and Dalhousie University, is considered the forefront of these types of technologies and capabilities. And AEM has been considered as a must-have tool for several of these types of customers and research organizations. And so in summary, AEM provides an accelerated path for battery electrolyte discovery, characterization, optimization. Genomic level predictions are enabled to cover molecular to macro scale properties that are key to several aspects of electrolyte performance. And then the applications are for fast charging, low temperature, and high cycling rates. So that's another area where, again, AEM and modeling simulation analysis tools is super powerful when some of these measurements are actually not feasible to be done either from a cost or time perspective. So AEM is a proven capability that allows you to explore these types of scenarios with high accuracy. And I guess, Kevin, on that note, do you have anything to add to the summary?
No, I think you covered it well.
So now we'll go ahead and thank everybody for their attention and participating in today's webinar. If there are any questions, we are happy to take those at this time, and we can also be contacted via email if anybody would like to send us those as well. Actually, we might have a question in the chat. Let's take it up. Oh, looks like our audio might have been. Yeah, we'll definitely fix that in the recording. Michael, thank you for bringing that to our attention. Any other questions? Yeah, how about from the Ridgetop team? Anybody got any questions? Okay. Actually, I might have one here that I did take a note. Let me see if I can find it. So Kevin, in one of the papers we have been studying, right, we know that AEM is very useful in being able to provide accurate measurements of transport parameters, such as the transference number and diffusion coefficients. So can you speak to why those are difficult to measure and why AEM is considered revolutionary for producing those types of data outputs?
That's a good point. So there's easy properties to measure, and then there's really difficult and expensive properties to measure in electrolytes. Some of the easy ones, you know, you might envision density is kind of a trivial, almost trivial to measure. Conductivity, you just have to have a calibrated meter and electrode. Viscosity, they make viscometers now that can do fairly quick measurements. But as you go into some of the more problematic property sets, you would find that diffusivity takes a bit more due diligence to get a number, and you have to be very, very careful with the context of setting up the type of measurement for diffusivity. So there's an electrochemical means to obtain diffusivity, and then there's also an NMR, pulsed field gradient, or PFG type method that is used. Those two methods aren't necessarily equivalent, and they don't always provide complete agreement. So it really just, you have to decide first of all your approach, and then you have to be very much aware of your boundaries within that. The transference number is another one of those that has different methodologies that have been tried in recent decades, and so you will find some variability between the different options there. What AEM provides is, I would say, more kind of middle road electrochemical type of basis for the transference number. So this is not uncommon, and also there's properties that are almost impossible to measure with any fidelity or with any degree of quickness, and like the desolvation process, those types of things. Also, when you go and look at like this microstate structure, sometimes that's handled with molecular dynamics, which is notoriously slow. When you look at the temperature range and concentration range that AEM handles for those types of calculations, it's quite literally an impossibility to do that with molecular dynamics. You'd be doing years of calculation compared to what AEM can do in less than a minute. So that's kind of the advantage of hard to measure or impossible to measure type quantities that AEM provides.
Yes, thank you. And maybe you can speak to about how certain electrolyte additive packages, they know they've been proven to extend the cycle lifetime of lithium-ion battery cells, but not for all temperature conditions or temperature ranges, right? So AEM allows users to investigate, you know, the effects of different electrolyte additives and how they can, what range of temperature conditions or operating conditions they may be relevant towards. If you want to speak to that a little bit.
Well, additives, in kind of the conventional use of that term, additives are used to enhance the passivation process of the electrode. So the surface to electrolyte interface that are formed on both the cathode and anode early in a cell's life are very much dependent upon the choice of electrolyte, and the additives. The AEM allows those additives to be input, at the kinds of quantities that you would expect. Generally, that's like between 1% and 5%. And so you get a true rendering of their impact on the electrolyte properties. But what the user needs to be aware of is that AEM does not predict the passivation outcomes of those electrolytes. That's another field of endeavor that has been discussed for eventually aiming the Advanced Electrolyte Model toward looking at the passivation consequences. But we're currently not there. So it's that aspect has to be tested. And so what we've learned is that we do design with AEM. We formulate the fundamental electrolyte composition. We test that in cells and check for compatibility. So if we're seeing good compatibilities, we'll see a fairly low aging rate, say over the first 150 to 200 cycles. And if there's any inconsistencies or incompatibilities between the materials, that generally should show up early, even during the formation cycling, which is very, very early in the cell life. So if we do see issues, we can back up and reformulate and use the AEM to do the reformulation, and then take it from there. We've used that approach to greatly accelerate our electrolyte screening for the fast charge program. And it usually takes probably no more than 2 iterations before we're kind of to the place of optimizing the electrolyte for the materials.
Yeah, fantastic. All right, and I guess just one more question before we do wrap up here is, can you speak to the benefits of the Dow Chemical evaluation of AEM and how they utilized it to reduce the number of experiments required to arrive at their new combination of salts and solvents using AEM?
Right. So Dow Chemical was kind of the first adopter some years ago, I must say. And what they were looking at, they were engaged in electrolyte discovery for the particular cell architecture that was their target. And I don't recall exactly what that was at the time. It was probably like an NCA graphite. If I were to dig a little deeper, I think that would probably be the one. So I'm trying to think of the total numbers. It seemed like at the end of the day, the AEM helped take like something like 3,000 possibilities of combinations and reduced it to a fraction of that, like say maybe 10% of that, at least, so that their testing burden was greatly reduced and greatly accelerated.
Yeah, absolutely. So yeah, we know that's one of the true benefits of modeling, simulation, and analysis tools is, being able to reduce the time and cost for developing those types of experiments, and then the time and resources it takes to actually execute and analyze the results, just to find out that that wasn't a valid experiment for the use case we were investigating. So,
right. Dow Chemical was also looking at some very unusual choices. So one of their salts was a dilithium salt, which is, you hardly ever see that in batteries today, but they were looking at a particular candidate that had some very unusual traits for using in battery systems. But they wanted to kind of go a little bit off-road on some of their choices, and so they used AEM in conjunction with INL to explore the consequences of choosing some of these more uncommon type of chemicals.
all righty. Well, I think that is time for today's webinar. We may be doing additional webinars for AEM in the future for some of our training and educational purposes. So if you have not already, feel free to subscribe to our newsletter and inform for that. And any additional questions that may come up, feel free to reach out to either Dr. Kevin Gering or myself. Our contact information is shown here on this slide. But we'd like to thank everybody for participating, and we were glad to introduce AEM and the new graphical user interface. And we look forward to supporting your battery R&D needs. So thank you, everybody.